Welcome to this explainer. Today, we're diving into the hidden mathematical engine that literally runs everything around us. I'm talking about the social networks we scroll through every single day, the layout of complex city maps, the whole shebang. It's this fascinating field that looks super simple at first glance, but quickly reveals these absolute, hard physical limitations that govern our very reality.
Think back to when you were a kid, or hey, maybe even doodling in a meeting yesterday. Have you ever tried that classic drawing puzzle? You know the one, right? Where you try to connect a series of dots or draw an intricate shape without ever lifting your pen from the paper, and here's the kicker, without letting a single line cross. It feels like just a fun little brain teaser, but without even realizing it, you were actually brushing up against some seriously high-stakes mathematics.
So to really get this, we've got to jump back in time. This entire field of math actually traces its roots all the way back to 1736 and the legendary Leonhard Euler. He was just trying to solve this local puzzle about whether you could walk across all the bridges in the town of Königsberg exactly once. Well, from that one simple, seemingly trivial riddle, the field saw some steady theoretical developments through the 19th century before absolutely exploding in the 20th century. Today, it's basically one of the most active, vital fields in all of mathematics.
Section 1. The anatomy of a graph. Okay, in rigorous set theoretic terms, a simple graph is defined as a pair. G equals V and E. V is just a finite set of vertices, and E is a subset of the two-element combinations of V, which mathematicians sometimes write as P2 of V, and we call those combinations edges. Now, I know that sounds like a whole lot of abstract mathematical jargon, right? But stick with me, we're going to make this incredibly intuitive.
Because what's really cool here is how easily we can translate that Greek into the real world. Think of the vertices, that capital V, simply as people, and the edges, capital E, as mutual relationships, like friendships or marriages. The whole point of these simple graphs is to encode relations on a finite set that are binary, meaning they happen between exactly two things, and symmetric, meaning the feeling is totally mutual.
Let's quickly lock in our vocabulary so we're fully equipped for the puzzles coming up. Vertices, or nodes, are literally just the dots in our network. Edges are the lines connecting those dots. When two dots share a line, we say they're adjacent, and if you're focusing on one specific dot, any other dot connected directly to it is called its neighbor. Pretty straightforward, right? That is the core anatomy.
Section 2. Math in action. Coprimality graphs.
All right, let's actually build what's called a coprimality graph, or COP-N. This is going to be our first real-world mathematical test case. In this kind of graph, our dots are simply numbers from 1 to n. And we only draw a line, an edge, between two numbers if their greatest common divisor is exactly 1, meaning they don't share any common factors other than 1. In math terms, they are coprime.
Let's walk through this step by step for the fifth coprimality graph. Step 1. We lay out 5 dots numbered 1 through 5. Step 2. We check the pairs. Take 2 and 3, for example. They share no divisors other than 1, so boom, they get a line. But 2 and 4, well, they're both divisible by 2, so their greatest common divisor is definitely not 1. No line for them. Step 3. We just keep doing this, drawing an edge every single time a pair is coprime.
And this perfectly illustrates what that looks like when we're done. We've arranged the 5 nodes in a pentagon shape here, and man, it's a bit of a messy web, isn't it? Notice all those multiple lines intersecting right smack in the middle. Section 3. Untangling the WEC.
Now here's the thing you need to remember. The mathematics of a graph only care about who is connected to whom. It doesn't care at all about where you physically place the dots on your page or how curvy you draw the lines. So I've got a challenge for you. If we mentally move these 5 points around, do you think we can redraw this exact same graph without any of those edges crossing in the middle?
Well, the answer is a resounding yes. Take a look at this. By simply repositioning the points, like dragging node 1 right into the center, for instance, we magically remove all the intersections. We've completely untangled the web, all without changing a single piece of the underlying mathematical structure. The connections are literally identical, only our visual representation changed.
Section 4. The impossible complete graph.
Now, allow me to introduce you to the ultimate boss level of simple graphs. It's called K5, also known as the complete graph with 5 vertices. In this network, absolutely everyone is neighbors with everyone else. Every single pair of distinct vertices is connected by an edge. No exceptions. When we draw K5 in its standard form, it usually looks like a star inside a pentagon. It's got this undeniably beautiful symmetry to it. Every node is perfectly equal, but look at the center. It is an absolute tangled mess of intersecting lines.
Okay, so let's try our previous trick, right? We try to reposition the points, we try bending the curves to untangle it, and here is our absolute best attempt at minimizing those intersections. We move things to the outside, we stretch the curves way out, but look right there. No matter how we bend things, we are stuck with exactly one final unavoidable crossing.
Seriously, imagine trying to draw this yourself on a piece of paper right now. Just 5 dots. Try connecting every dot to every other dot. Go ahead. Trace it in your mind for a second. Can you connect them all without a single line jumping over another? It really feels like there must be some clever little trick you're missing, right?
But there is no trick. As mathematician Darge Greenberg points out, quote, "This is a question of topology, not of combinatorics. The answer is no," end quote. No matter how long you sit there trying, no matter how you draw this graph on a flat plane, you will always have at least one pair of curves intersect. It is mathematically impossible.
So why is that? It's because we are strictly bound by the physical rules of a 2D plane. Curves drawn on a flat piece of paper absolutely must be continuous. Unless you break the fundamental rules of reality, lines can't just teleport or magically jump over one another. J5 isn't just a fun puzzle, it's a proof of an absolute physical limitation. It reveals the hard boundary of what can physically exist on a flat, two-dimensional surface.
Section 5. Beyond the dots and lines.
So what does this all mean for us? Why does it matter? Well, think about it. If a relatively simple 5-node complete graph cannot physically exist on a flat plane without intersecting, what does that mean for engineers who are designing real-world computer microchips with billions of tiny pathways? Or what does it mean for urban planners trying to lay out massive, complex subway lines and city grids on the flat surface of the Earth? They are fighting against the exact same topological roadblock we just explored. It really leaves you looking at flat surfaces, circuit boards, and maps with a whole new sense of mathematical wonder, doesn't it?